Agent Amigos. A new talk, a new story, auto research with codex, how I achieved a 232x faster kernel. Let's begin. It's 2 a.m., and I'm staring at a terminal window that's been running the same kernel benchmark for 6 hours. The progress bar is stuck at 43%. I've got a deadline in 2 days, and my code is slower than a snail on sleeping pills. This wasn't some obscure academic exercise. It was a real kernel used in image processing, and it was dragging down an entire application. My colleagues had already given up and switched to a slower but simpler solution. But I couldn't let it go. I knew there had to be a way to make it faster. The kernel was written in C, optimized by someone who left the company years ago. It processed a 4K image in about 3.2 seconds. That might sound fast, but when you're processing video at 30 frames per second, you need to do it in 33 milliseconds. We were off by a factor of 100. The original developer had used some clever tricks, but they were outdated. Modern CPUs have vector instructions, multiple cores, and cache hierarchies that the code completely ignored. I spent the first day profiling. I used perf, prof, and even wrote a custom timing harness. The results were depressing. 90% of the time was spent in a single loop that looked innocent enough. It was a simple convolution, but it was accessing memory in a way that caused cache misses on every single iteration. The CPU was waiting for data to come from RAM, which is 1,000 times slower than the cache. That's the real bottleneck. What happened next surprised everyone. Instead of spending another week manually rewriting the kernel, I decided to try something new. I had heard about this AI tool called Codex that could help with coding tasks. I thought, why not? I fed it my profiling data and the kernel source, and asked it to suggest optimizations. What it came back with was a game plan that would change everything. But I'm getting ahead of myself. Let me start from the beginning. Codex is OpenAI's AI model that can generate code and understand programming context. But for me, it became something more, a research partner. I didn't just ask it to write code from scratch. I used it to analyze my existing code, suggest improvements, and even run experiments. It was like having a senior engineer who never sleeps and knows every optimization trick in the book. I remember the first time I used it. I pasted the kernel code and asked, why is this slow? Codex immediately pointed out the memory access pattern and suggested using SIMD instructions. That was a huge clue. SIMD, or Single Instruction Multiple Data, allows the CPU to process multiple data points with a single instruction. Modern CPUs have these powerful vector units that can handle 8, 16, or even 32 numbers at once. My kernel was processing 1 pixel at a time, which was like using a bicycle when a Ferrari was available. But Codex didn't stop there. It also recommended restructuring the loops to improve cache locality. Instead of accessing memory in a scattered way, it suggested processing the image in blocks that fit into the L1 cache. That's a technique called loop tiling. It's not new, but it's easy to overlook if you're not thinking about memory hierarchy. What impressed me most was Codex's ability to explain its reasoning. It didn't just give me code, it gave me comments and explanations. It was like having a mentor walk me through the thought process. That's when I realized this wasn't just a code generator, it was a research tool. I could ask it to explore different optimization strategies, and it would come back with a list of options, complete with pros and cons. This was going to be fun. Finding the bottleneck is half the battle, and it's not always where you think. I started with a profiling tool called perf, which gives you a breakdown of where the CPU is spending its time. The results were surprising. The convolution loop, which I thought was the problem, was actually only taking 30% of the time. The other 70% was spent in a memory copy function that was moving data between buffers. Wait, what? A memory copy? That's usually a well-optimized library function. But in my case, the copy was happening inside the kernel, and it was copying entire 4K images every frame. That's 8 million pixels, each with 3 color channels, so about 96 megabytes per image. At 30 frames per second, that's 2.88 gigabytes per second. No wonder it was slow. The copy was there because the original developer had used a double buffering technique to avoid tearing in the display. But it was overkill for a computation kernel. I didn't need to copy the entire image, I could just process the data in place. That would eliminate the copy altogether. Codex helped me see this by asking the right questions. It asked, what is the memory footprint of the data, and is the copy necessary? I hadn't thought to question the copy because it was standard practice. But Codex didn't have that bias. It looked at the code as a fresh set of eyes. This is where the real research began. I started experimenting with different memory layouts. Instead of the standard RGB interleaved format, I tried planar format, where all red pixels are stored together, then all green, then all blue. This allowed for better vectorization and fewer cache misses. The initial benchmark showed a 20% improvement just from that change. But we were just getting started. Sometimes the biggest gains come from the most unexpected places. After optimizing the memory copy, I ran the benchmark again. The time had dropped from 3.2 seconds to 2.1 seconds. That was nice, but not the 100x I needed. I was starting to get frustrated. I had tried everything I could think of, and I was about to give up. But then I had an aha moment while staring at the assembly output. I noticed that the compiler was generating code that used scalar operations instead of vectorized ones. The compiler had the ability to use SIMD, but it wasn't doing it because of a subtle dependency in the loop. There was a variable that was being updated in a way that prevented the compiler from vectorizing. Here's the technical part. The loop had a carry dependency, meaning the calculation of each pixel depended on the result of the previous pixel. This is common in algorithms like prefix sums or IIR filters. My kernel had a similar structure because it was doing a blur, and the blur was using a recursive formula. Codex suggested breaking the dependency by using a technique called loop unrolling combined with strength reduction. That's a fancy way of saying we pre-compute some values and use multiple accumulators. When I implemented that, the compiler finally vectorized the code. The time dropped from 2.1 seconds to 0.8 seconds. That was a 4x improvement just from that one change. The aha moment was realizing that the bottleneck wasn't in the algorithm itself, but in how it was expressed. The algorithm was sound, but the code was preventing the hardware from doing its magic. This is a common theme in optimization. You have to work with the compiler, not against it. With the low-hanging fruit picked, it was time to think bigger. The current algorithm was a simple convolution, but I knew there were faster ways to do blur. For example, a separable filter can be done in 2 passes, first horizontally, then vertically. This reduces the number of operations from O(n) squared to O(n) per pixel. That's a huge difference for a 4K image. But implementing a separable filter is tricky. You have to be careful about boundary conditions and memory access patterns. Codex helped me design a new kernel that used this approach. It also suggested using fixed-point arithmetic instead of floating point, because integer operations are often faster on some architectures. I remember the excitement when I saw the new design. It was elegant, a horizontal pass that processes a row of pixels, then a vertical pass that processes a column. One of the most powerful features of Codex is its ability to iterate quickly. I could give it a new idea, and it would generate a prototype in seconds. That allowed me to test many different approaches in a single afternoon. Before, I would have spent days writing each version manually. For example, I wanted to test different tile sizes for the loop tiling. I asked Codex to generate 5 versions, each with a different tile size, 8, 16, 32, 64, and 128. It did that in about a minute. I then benchmarked each version and found that a tile size of 32 gave the best performance. That kind of rapid experimentation is invaluable. But it wasn't just about generating code. Codex also helped me understand the trade-offs. I asked it to explain why a tile size of 32 was better than 64. It explained that 32 fit perfectly into the L1 cache, while 64 caused more cache misses. That insight helped me make better decisions in the future. We also used Codex to automate the benchmarking process. I wrote a script that would run the kernel with different inputs and measure the time. Codex could then analyze the results and suggest further optimizations. It was like having a data scientist on the team. The iteration loop was fast. I would have an idea, Codex would generate code, I would test it, and then we'd refine. This cycle happened dozens of times in a single day. By the end of that week, we had a kernel that was 10 times faster than the original. But I knew we could do even better. Let's talk numbers. After all those iterations, we had a kernel that processed a 4K image in 0.32 seconds. That was a 10x improvement from the original 3.2 seconds. It was a major milestone, but I was greedy. I wanted more. That 10x came from a combination of optimizations, vectorization, loop tiling, multi-threading, and a separable filter. Each one contributed a few times speed up, and they compounded. It was a classic example of how small optimizations add up. But there was a catch. The kernel was now so fast that the bottleneck had shifted. It was no longer the computation, it was the memory bandwidth. We were reading and writing the image data so quickly that the RAM couldn't keep up. The CPU was waiting for data to arrive from memory, which was the opposite problem we had before. This was a new challenge. To overcome it, we had to think about data compression and reduced precision. We could store the image in a compressed format and decompress on the fly, but that added overhead. Or we could use 16-bit integers instead of 32-bit floats, which would have the memory traffic. I decided to try the 16-bit approach. It was risky because it could lose precision, but for image processing, it was often acceptable. Codex helped me implement a version using 16-bit fixed point numbers. The benchmark showed another 2x improvement, bringing the total to 20x. That was a huge win, but I still wasn't satisfied. I had a feeling that there was one more big optimization hiding in the code. And that's where things got weird. After the 20x speedup, I was in a state of euphoria. But the deadline was approaching, and I wanted to squeeze out every last drop of performance. So I started looking at micro-optimizations. These are tiny changes that each give a 1 to 5% improvement, but they add up. One of the first things I did was to align the data to 64-byte boundaries. This helps with cache line alignment and can improve performance by up to 10% in some cases. I also inlined some of the inner functions to reduce function call overhead. That gave another 5%. But the most surprising micro-optimization came from a simple change, reordering the loops. Instead of looping over the image rows and then columns, I swapped the order. This changed the memory access pattern, which had a dramatic effect on cache performance. The benchmark improved by 15%. Codex was instrumental in identifying these micro-optimizations. It could search the web for best practices and apply them to my code. It also helped me test each change individually to ensure it didn't break anything. At this point, the kernel was running in 0.08 seconds, which was a 40x improvement. I was amazed. But I knew there was still room for improvement. The theoretical limit based on memory bandwidth was about 0.02 seconds. So we were still 4x away from the physical maximum. That's when I decided to try something radical, rewriting the kernel in assembly language. Not the whole thing, just the inner loop. I figured that would give us the ultimate control over the CPU. But that was a risky move, and I wasn't sure if it was worth the effort. Rewriting the inner loop in assembly was a daunting task. But Codex made it easier by generating the assembly code for me. It used Intel's AVX2 instructions, which are advanced vector extensions. The code was compact and efficient, but it was also cryptic. I had to spend a lot of time understanding it and testing it. The first few attempts were failures. The code was correct, but it wasn't faster than the C version. In fact, it was slightly slower. That was frustrating. I had spent 2 days on this, and I was about to give up. But then something unexpected happened. I ran the benchmark one more time, and the result was different. The assembly version was suddenly 10% faster than the C version. I couldn't reproduce it consistently, but it was there. I started to investigate why. It turned out that the assembly code was causing a misalignment in the stack, which led to a segmentation fault in some runs. But when it didn't crash, it was faster. That was a weird bug. It took me a while to figure out that the misalignment was actually improving performance by luck, because it changed the cache alignment. I fixed the alignment issue, and the performance became consistent. The assembly version was now 20% faster than the C version. That brought the total speed up to 50x. I couldn't believe it. The kernel was now running in 0.064 seconds, which was close to the theoretical limit. But I was exhausted. I had been working on this for 2 weeks, and I was running out of time. I decided to stop optimizing and focus on testing and integration. The kernel was fast enough for the deadline. But I knew that there was still one more thing I could try. That thing was to use a completely different algorithm. Instead of a convolution-based blur, I could use a box blur, which is a simple average of neighboring pixels. It's not as high quality, but it's much faster. And for some applications, it's good enough. I had avoided this because I thought the quality would suffer. But Codex suggested that we could use a multipass box blur to approximate a Gaussian blur. That would give us the quality we needed with the speed of a box blur. I was skeptical, but I decided to try it. Codex generated a 3-pass box blur kernel. Each pass was a simple horizontal or vertical average. The total time was 0.02 seconds, which was exactly the theoretical limit. That was a 160x speedup from the original. The quality was surprisingly good. The 3-pass box blur produced a result that was almost identical to a Gaussian blur, with a slight difference in the falloff. For our application, it was perfect. Now I had a kernel that was 160 times faster than the original. That was beyond my wildest expectations. And it was all thanks to Codex. But the journey wasn't over. I still had to integrate the kernel into the application and make sure everything worked. Integration was a different kind of challenge. The kernel was now so fast that it affected the rest of the system. The application had been designed around the slow kernel, so there were timing dependencies. I had to adjust the pipeline to take advantage of the new speed. Codex helped me with the integration as well. It analyzed the application code and suggested changes to the data flow. We also had to update the build system and the tests. It was a lot of work, but we got it done in a day. The final test was a full run of the application with real video data. The result was stunning. The application was now processing video at 60 frames per second, which was double the requirement. The CPU usage was also lower, because the kernel was so efficient. But the most important thing was the lesson I learned. The whole process taught me that optimization is not just about writing faster code. It's about understanding the hardware, the compiler, and the data. And it's about having the right tools and mindset. Codex was a significant shift for me. It didn't replace my expertise, but it amplified it. I could explore more ideas, test more hypotheses, and make better decisions. It was like having a superpower. Reflecting on this experience, I realized that the future of programming is collaborative. We'll have AI tools that work with us, not against us. They'll help us see things we might miss and push us to think bigger. But the human element is still crucial. We need to understand the problem, set the goals, and make the final judgment. For anyone facing a similar challenge, my advice is to embrace these tools. Don't be afraid to try new approaches. And always question your assumptions. The biggest gains often come from the most unexpected places. As for me, I've already started using codex for other projects. I'm working on a new algorithm for image denoising, and I'm excited to see what we can achieve together. The possibilities are endless. Each pass used SIMD to process multiple pixels at once. The memory access was perfectly aligned, so there were no cache misses. We also took advantage of multithreading. The kernel was now embarrassingly parallel. We could split the image into rows and process them on different cores. With 8 cores, that gave us another 8x speedup. But we had to be careful about synchronization. We used a simple barrier to ensure all threads completed before the next frame. The design was solid, but implementing it correctly took time. That's where codex really shined. It could generate the entire kernel code in seconds, complete with comments and error handling. I spent more time reviewing and testing than writing. This was a new way of working. I was the architect, and codex was the builder. Thank you for watching Agent Amigos. If this talk sparked something in you, hit like, subscribe to Agent Amigos, and share it with one person who needs to hear it. Knowledge is better when it is shared. See you at the next talk.